Let me see. So I think these questions are still not for the superconductivity part. Am I right? Hyunjung. Print.
Yeah, that's with the reading of the
okay. So then let me. Don't know how we stay on with time. Am I behind? Am I?
No, it's good. You can share the.
Yeah, I'm trying. I just it doesn't let me switch the screen. So maybe I need to say stop share. Somehow
yeah, you can stop sharing and reshare. Yes.
Yeah, I will stop share and then.
In fact, it's better if you share the desktop because then you can both, show the Frontera and show the PDF.
I think that's what I did, but somehow with the I couldn't unshare after that. Okay, so let me just do that. One moment. Let me make sure that my screen on Frontera is still working. Yes. So so let me start sharing again. Share, and then I put desktop. So right now you should you are seeing the PDF file. Am I correct?
Yeah, correct.
So I'm not going to do it full screen just so it's easier for me to change between two images. So first example that we are going to do, as I said, it's on LED. So and please for questions, if you want some more detailed questions and they cannot answer in the main room, Hari Paudial and Gianu Kafle will help you in two of the breakout rooms. Yeah, so they helped me do that with this tutorial, and they could answer questions. So first, what you need to do is to go on Scratch, and that's what I'm going to do. Just to get started, I will follow the same steps with you. And
specifically, you can go to room 2 if you have a question. Ari is in room 2, just to be specific.
Ari is in room 2, and Giano, can you see him in which room he is?
He's not.
It's not, okay. Okay, in my case, it says McDeary didn't because I already had a directory called epw.school, and probably you should also have it since you did that on Tuesday. I think Yun Jung had the same setup. So now if you are going in this directory, you will see that you should have a tar file. And then I'm going to remove my old file since it was already there. And then I'm just going to untar this just to make sure that's the same as the one that you are using right now. But the step you shouldn't do is just this. Yeah, and then we can go in the first exercise. So I separated in two different directories the calculations that are related to phonons, and then the calculations that are related to EPW. Yeah, so if the first two steps here are exactly the same steps that you already did on Tuesday and Wednesday. Yeah, so in the first step, there is a batch script is provided that will run the SCF and the phonon calculation. Yeah, so all we have to do here is to go in the phonon code and just say s batch job.ph. And hopefully this will run in, and it should only take a few minutes. So once, so the results here in principle, you could have also copied the save directory to do this step from Samuel's calculation from yesterday, from exercise 1, since we are using the exact same input files for SCF and NSC and the phonon part. So once we run the phonons, you are going to gather them in this using this Python script, and this will create the save directory. And then we are going to move into the other directory called EPW. And there we need to provide to do the NSCF calculation. Now, I didn't mention here as a step, but if you do it in separate directories and you don't have the charge density file, you need to rewrite, to rerun the SCF calculation first, or you can copy them from your Phonon directory. Yeah, so in the current script, although it's not mentioned here as a step, if you look in the SBatch job, in the job EPW1, you will see that the first thing is that we rerun the SCF calculation. And this is, as I said, just to generate the charge density, because this is needed for the NSCF calculation. So not found. So let me see if the job has finished. I think it is finishing. Something. I did finish. I don't know why it's still showing here. Okay, so now I can collect the files using the Python script. In this case, the prefix is LED, and then I have made this save directory. And then next, I'm going to move into the next directory called DPW. Yeah? So I do cd DPW, and then here, first job script. As I said, the first step, it runs the SCF. So I will just submit it because this will take a bit of batch, which I misspelled. Job 1. So here, let's look a bit through the input file. So the NSCF, as I said, is the same. We are going to use, I believe, a 6x6 K mesh, and the Phonon was a 3x3x3 Q mesh. And for the EPW calculation, we are first writing the electron-Phonon matrix elements, and then we are solving. We are writing also all the Eliashberg electron-Phonon coupling files, and then we are solving the isotropic Eliashberg equation first on the imaginary axis and then on the real axis using both PADE and analytic continuation. And these are the thresholds for convergence for the self-consistency. This is in the case of the imaginary axis. This is the convergence threshold for the real axis solution. And then here, as I said, this is the cutoff, the upper limit over the Matsubara frequency. This is mu star. And in this case, as you can see, because I don't have, at some point, the temperatures are not evenly distributed towards the upper part of the gap at highest temperature, I'm providing them as a list. And we are using a MP mesh K true. So in other words, we are using the irreducible electronic phi mesh, and this is the mesh on which the calculation will be done. So if we go to the setting and let's see if my job is running. Hopefully I am already. We can see what happens. So yes, so the code has done the vanirization. Yeah, you can see that the orbitals are very well localized. This is the spread in the varnierization, and this is the calculations on the coarse Q mesh. Yeah. These are the points, and then that's where the code starts doing the interpolation. Yeah, so this information here, we provide information about the uniform mesh, 18 cube, the information about the uniform mesh for electrons, also 18 cube, and here it's MP says that we are basically using this MP mesh K true. This gives information about the Fermi energy on the coarse grid, and this also provides information about Fermi energy on the fine grid. Yeah, so you can see that these calculations are really not converged. The differences between these two should not be significant. Yeah, so don't take this as a converged calculation. And then this is progression on calculating the electron-phonon matrix elements, basically on the fine K and Q mesh. And the progression is shown as we go from different, since the outer loop in the code, it's over Q points. So once this has finished, we can see some additional information here. This is it says that, should have said somewhere that we finished writing yes, here it was finishing writing the EPH math files. Then once we have the Eliashberg reflect true, the very first step, as I said, is to read the files that were written in prefix EPH math directory. And then once that is done, the electron-phonon coupling strengths are calculated. And here in the output file, we only print the isotropic electron-phonon coupling strength. And we also print a value for estimated TC using the Macmillan-Allendine equation. And in fact, we also estimate the BCS superconducting gap, since this is basically internally, it's an input for the initial input in the solution of the self-consistent solution of the Eliashberg equations. And then the following information here is, it tells you that you have started solving the Eliashberg equations in the isotropic case on the imaginary axis. Yeah, so this is the iteration number in the self-consistency. This is some error in the iteration, and this Z norm and delta I, these are the Z value at omega equal to 0. And in this case, it says that it reached convergence in 8 iterations. Then it does an Padé approximation. The Padé is a single step. So it also prints how many points, approximants were used in the Padé approximation. And then it prints the value of the gap, the real and the real value of the gap and the real value of the Z norm, again at omega equal to 0. And then this is for the analytic continuation. Yeah, so in this case, again, I said this is a self-consistent thing. This is the iteration number. This is the error in the convergence. So yeah, if you remember the threshold, we said that we tend to -4. So and then these are again the real part and the Z and delta. And the same thing you are going to see printed out at every single temperature. So I think the code is still, maybe it has finished now. Yeah. So it has finished now. So you should have, hopefully all of you gotten the same results at every temperature that was given in the input file. And you can see here, as I said, there are a bunch of files that are generated. So the last index in the file corresponds to the temperature. So if you go now the exercise, you should be able to, so I go down, we should be able to do to make some plots. And the description of the file is also given here. Yeah, here it specifies every single file, what each column of the file contains. And that's a no plot. Right now, if you will need to copy basically, or it's up to you. Maybe you are using some other graphical program to look at the plots. But if you use this script and you copy and paste every line, yeah, make sure that when you copy, you just take the part from no plot. If you plot this file, this specific files, you should get the plots that you are shown here, yeah, with the data or with the input variables that we have just given to the input files. Yeah, I'm not going to do this step just because it takes too much copying and pasting, but that's the plot that you should get. At convergence, you should get something more like this. Now, one thing that I didn't describe before is that, sorry, you can also plot the leading edge of the superconducting gap. And for this, Harry has provided this small script, which I think you probably need to copy and paste it. Let me see. Or it's already existent in the, oh no, they are already here. So you can see that you have all these small scripts, bash scripts, that, that you can use to extract the data. So if you do that, you can extract from all temperature files, you can extract a file that will have the leading gap. Yeah. So you just need to run this script here. So if you do that, you will obtain a new file with this name and with new plot. If you plot it, you should get this curve showing here on the left. Let me look in the chat a bit, since I've been talking for quite a while, and not sure if, I think Samuel has left this room. I'm not sure if anybody is answering.
I'm back.
Oh, you're back. Okay.
Fine. I was helping in a breakout.
No, thank you. I just want to see if there are questions that because I'm talking and nobody stops me. So let me see where we are. Okay, let me see. Jorge had a question about imaginary. I'm not sure how. Where was the last question that I answered? Okay, Simone, I think maybe you can go. I'm not 100% sure. I think Harry may have some answer to this question, but indeed it can become a bottleneck when you want to run calculations of low temperature because of memory issues. So, or maybe Samuel, do you know how to answer this question better? I know that one way is to request more nodes and not use all of them.
I cannot see the question. I think when they are typed and I'm away, so I don't think.
So it was. So it's from Simone. It says, in my experience, when running on very dense grids, the RAM usage can become a bottleneck, usually at lower temperatures when there are more Matsubara frequencies. Do you know which parameters affect the RAM usage more heavily? I mean, I mean, when we store, I mean, in sense, which parameter is hard to say, because on every core, we save the matrix elements that are a multiple of, basically it's an array that has 5 or 6 indices. I don't remember, K, Q, number of bands, number of phonons, and then times number of Matsubara points, and they
Yeah,
are
so that's the reason. So if you have a lot of Matsubara, then
yeah.
you
So if you have if you keep the other constant, that's what I want to say. If you keep the other constant and you multiply, increase the number of Matsubara points, that may be the. I mean, that's going to be the bottleneck in that case. But also, if you increase the mesh, Q mesh and K mesh, and you don't increase the number of cores, you are also going to increase the number of elements that you are going to store. Okay, another question. If I get a small negative frequency calculation, will it be excluded afterwards? So that depends if you have used the acoustic sum rule, and you will need to plot if you the phonon dispersion. So if you plot with the acoustic sum rule, you need to see this will be with Q2R and Margine if your all phonons are going to be positive. And then in EPW also we can use ICR a simple or crystal, so you will get the same results as in the phonon codes. Any negative phonon mode is going to be ignored. Yeah, so there is and that's valid for other parts of the code. Also, there is an if condition that it only takes into account phonon modes that are above a threshold. And that's a parameter in the code that I think right now it's like 5 milli-electron volts, if I remember correctly. Okay, if we do not know the value of TC, the code crashes if the temperature is greater, obviously. Is there a way to estimate before? Yes, so that's why you, first of all, even if you don't use this TS linear true, as you saw at the end of the calculation, just with Eliashberg, you have this Allandine TC. So that's going to give you an idea about the critical temperature. Although you need to keep in mind that if, let's say, if you do a calculation for MGB2 with the isotropic case, you will get a TC of 20 or 25 Kelvin. And obviously that TC is much larger. So the code, so if the provided TC is larger than the Allandine, the code will give a warning, but it's not going to crash or not going to stop. It's really going to stop only if it gets to a temperature where the solution, the equations have no solution. Yeah, and that point is not going to converge. Eli, since you anyway calculate phonons with quantum espresso, you could run, yeah, that's also true. You can get an estimate from quantum espresso. So in the PADE approximation, there is no iteration. It's one-step procedure. Simone, currently only array is distributed only Q points. We need to distribute array. Okay, I think Hyunjun has answered. I think we are, we don't have any more questions so far in the chat. Okay, so I can then continue a bit with the tutorial. So the second part, so these are plots. This sixth step, as I said, is if you want to see how this feature works to solve the linearized equations. And in this case, you can run this second batch script. And this is done, I think, by reading. So that's one option that you can do in the isotropic case. In fact, not only when you solve for the linear TC, but even if you want to solve the isotropic equation. So in this case, because if you remember, I can go back here, the equation in this case only depend on this lambda, which is basically dependent on the Eliashberg spectral function. So really to run this equation, you don't need to have this electron-phonon matrix elements to file. So if you want to solve just the isotropic case, all you need is an Eliashberg spectral function. And that you can start from that and you can read basically that file. And this you can do, you only need a single, basically a single node. Yeah. So if you want to just to look at isotropic case, this is really, really cheap as long as you already have a file with the Eliashberg spectral function. So all the steps that we did here before, if you would have, let's say, taken the file that you calculated on Wednesday for the lead case, we could have done the job, the previous step, starting from that file. So here, yes, if you are gonna do this part, you will get something like this. Yeah, this is only 475 Kelvin. If you are gonna do more converged calculation, you should get a value at about 6.6 Kelvin. So I'll move to exercise 2. So NS iter, this is number of iterations. Let me see. I was referring for analytic continuation. Is the same. You are basically iterating the same as you do in the on the imaginary axis. You have a set of equations. If you go in our PRB reference, they are written there, but you have basically an equivalent set of equations on the real axis that you will need to need to be iterated self-consistently. They look more or less the same, plus some extra terms. Okay, sorry here. Let me now go to, no, I wanted the tutorial here, to the second exercise. So this is second exercise is on MGB2. So the first part, again, you will need to run the phonons. I'm not going to describe those files anymore. So they are exactly the same. So we need, we just need to run them to get the phonons. And once we get the phonons, we can collect them. And then we can move on to the next step to do the Eliashberg calculations. Barbara, I mentioned, and let me give you, I mentioned that the files, if you are still there, they are on the EPW website. Which I don't see right now. EPW. So I'm not sure, Barbara, if you are here. Let me see if or if she is in a different room.
I remember last time I was looking, there is very nice.
So if you go here under documentation,
yeah,
it's not really under input variables. So you need to. Can you see my website?
There is
so
only input description.
No, but if you go under, if you go under documentations and you go here tutorial, there are examples, and you see if you click on MGB2 examples, that gives a description. It's more or less the same steps of the exercise 2, and then here it gives this description of every single file. So it's here documentation. Under documentation, not under inputs. Inputs indeed gives just the variable. You need to go here tutorial.
Yeah, but I mean, maybe it would be useful to have like outputs, like the other code, like Schenk BTE has outputs too. But you are too more very complex code, yeah.
I see what you are saying. Just to have like a full page just with output files. Okay.
Output files, or even the name, what each file does or something. Yeah,
I see.
So this was very useful what you were showing. Yeah, thank you.
Thank you. But that's a good point. We'll keep in mind that things when we'll be updating the website in the future. So let me see if my calculation has finished. Yeah, I think it did. So now I can select the files with the Python script. And in this case, the prefix is MGB2. And when all this is done, I can move in the EPW subdirectory. And here I will just submit just again, this is a bit longer, takes a bit longer time. I'm going to submit job 1. And it has started. So, okay, let's just go a bit through the input file for the EPW part. So the relevant flags here, as I said, is the relevant flags are here. Eliashberg true. In this case, we said ln iso true. As I said here, I just did PADE. Analytic continuation would really be very, very expensive for an anisotropic case, although, as I said, the method is implemented inside the code. Then this is the number of iterations, and this is the convergence threshold in the self-consistency. This is the cutoff, so here it's set to 0.5, for instance, in this exercise. And I don't know why mu star is picked this small 0.05. Shouldn't be this small. In this case, you see that the temperature are evenly distributed. So right now we are just doing 3 temperatures between 10 and 20. Yeah, so that's what the first job script is going to do. And these were the coarse meshes, and these are the fine meshes that we are using in the current exercise. So let me go through the files. Again, that's similar output in the code that you will see. And in this case, we are also going to have more files. Yeah. And as I said, there is a cube file that will be generated. And in this case, there will be an index, y. And in this case, it's the band index. So that will be depending on how many bands we have within the FSTIC that we choose. And in order to get this file, we need to set Fermi plot true inside the input file. Yeah, and the code is going to calculate all these anisotropic values that I mentioned, the anisotropic electron-phonon coupling strength. And as I said, in fact, what you get in the file is just the value for omega j equal to 0. And as I said, this will represent the strength of a pair of electrons at the Fermi surface. If you get this lambda nk, this will be the band and wave vector dependent, if you want to call it electron-phonon coupling. And this is useful basically if you want to plot the electron-phonon coupling strength on the Fermi surface. Yeah, similarly as you plot, we can plot the gap. You can also plot this value on the Fermi surface. And then finally, you will get the isotropic electron-phonon coupling strength lambda and the Eliashberg spectral function. And yeah, these are the same equations in the other presentations. let's get to where we are going to plot something. So this 4-step GB2 basically shows how to, it gives some GNU plot scripts to plot this plots for lambda. Yeah, so if you use this script, you should be able to get the plots showing here in figure 5. Yeah, so this is the first plot will be for this figure. This second script will be for the middle figure, and this plot will be for this left figure. In this file, in fact, if we look, and let me open the file, because somebody asked at some point about smearing. So this is MGB2 A to F. You see that there are many columns. And at the end of the file, I think there is some information in the now at the beginning. The first column is the frequency. Then the next 10 columns are the Eliashberg spectral function, and the last 10 columns are the integrated Eliashberg spectral function for each A to F. And the 10 is because we use 10 smearing values. This is the default. You can change the number from the input. And the columns at the bottom here, the last lines, this line here gives the integrated electron-phonon coupling as a function of smearing. So you can see that once you increase the smearing, this total lambda doesn't change that much. Yeah, and this other line, this provides the information for what smearing value was used for each of these calculations. And this also provides the electron smearing. This is the d Gauss W that was in the input file. Yeah, so this only it's for one value. That's the Fermi window that we used. And this is the summed electron-phonon coupling. But the difference between sum and integrated is basically, it's in here, that integrated, what we did, we really used the Eliashberg spectral functions like this, where it's a continuous omega, and the default is 500 frequency steps. And then you integrate this, it's I to F divided by omega times 2, and this will be your lambda. The other one that says summed lambda, it's basically if you just use this equation 6 here. Yeah, so we'll just have a sum, and in fact, this is for omega equals 0. What I want to say, it's something like this. You just specify them. So this is for omega 0, so it will be 2 divided by omega q times the electron-phonon matrix square, and then times the delta functions, roughly. Yeah, so you will do it not on a continuous omega, but at the specific frequencies on which the phonons were calculated. And this is why we call it a summation, but the values, if they should be pretty close to the integrated values. Let me see if there is one question in the chat. In the PB case, the superconducting gap is a number at each omega, but in MGB2, it has many values at each omega. Width decreases, width increases. Okay, so in MGB2, let's go back a bit to the presentation. In MGB2, we are solving these equations. Yeah, so you see that there is no index, no band, and K index. So at every temperature, you are only going to have one value at every omega. Yeah, so that's why we get this plot. In the and then from here, if you take this value in the omega equals 0 limit, you'll get basically 1 dot at every single temperature. In the anisotropic case, you are solving at every omega, you have as many bands you have in your Fermi window and as many K points. Yeah, so you have this. So at every omega, you are printing values for every N and every K. Yeah, so depending on how many states and how many K points, that's how many values you are plotting. So if you were to look, if you were to plot the files, at every omega you have all these dots. And then what happens here is that this file basically just takes the value at omega equal to 0, and it normalizes them in the sense that it counts how many real points, because here some may be overlapped over each other, how many points have this value, how many points have this value. So this is kind of a normalized way of plotting. And as you decrease the temperature, you have basically the band narrows down, because in the end it needs to get to 0 as you get the critical temperature. Okay, let me see where we're left here with the presentation. So I think I was discussing the lambda plots. Yes, I think I was here. So also there are a few new plot scripts provided to print, to plot the gap. Yeah, be careful, this file, as you can see here, is going to be quite large, about 70 megabytes. So you may not want to plot it, just to make sure that your code is not, your window is not crashing. Yeah. And this is the same files at convergence, but as I said, these files are trimmed. About 50% of the points are shown. Yes, I guess that sixth step is important, how you can do a star calculation to compute the superconducting gap on the imaginary axis. And I think this is important because sometimes, yeah, you may want, first of all, you may not know exactly what the TC is. Also, maybe you cannot afford to do all the temperature calculation in one run, or you may not want to have an even distribution of temperatures. So there must be a number of reasons you want a restart, or sometimes maybe you just want to plot the gap on a Fermi surface to get the gap on the Fermi surface for a specific temperature. So in order to do that, you need to use this flag, imag read _ true, and you need to have the files for the, so the temperature, the first temperature in your list is going to be the temperature at which you are reading the files. Yeah, so you need to have a file with gaps at the temperature where the code can start from. And then the next temperature is going to be the temperature at which the new solutions are going to be provided. Yeah, so I think here, in fact, let me go in this presentation. I had a few notes about imag read. So as I said, it allows the code to read from the file the superconducting gap and the renormalization function on the imaginary axis at a specific temperature. And for this, you need to have the file at the temperature that it's going to be your starting point, yeah, the one that you want to read from. And this will be the first in your list. And then if you do this, you can use it to solve the anisotropic equation. As I said, temperature is greater than your starting point, or you can, maybe you haven't done the analytic continuation to real axis. Maybe for a specific temperature, you just want to do the real axis to get the real axis solutions. Or, as I said, maybe you only want to get the file with the superconducting gap on the Fermi surface in the cube format, which is only written if you set up iverbosity true. Usually you may not set this flag true. Yeah, so this is the reason why this flag could be useful. Let me look again in the chat. Niraj, I would say that you don't have to solve right away the anisotropic equations. first I would only do a calculation of just having the flag Eliashberg true. And I would first really check these files, the lambda, plotting these files. This already should give you some idea about anisotropy in your system. Yeah. Is rho, yes, yeah, rho and lambda, it's again, this is also normalized to the largest value. Yeah, so it is indeed a distribution of lambda values. Okay, let me go back to this slide. Okay, so I think we were at this point where I said that in principle you can use the there is a script here just to see how you can get the leading, you can get the superconducting gap for MGB2. Yeah, so in this case, you will get something like this. I think somehow this file doesn't, oh no, okay, we have a bunch of temperatures, 10, 20, but I think this probably was with a restart. Yes, okay, which I didn't do yet. So I also need to submit the second script. And if you do that, you will restart from 10 Kelvin and you will get the solution at this additional temperatures. So once you have that, you can use this, this script to plot different files, different temperatures, and hopefully you should get a plot like this. You see that there is a lot of noise. This is definitely not converged. You can also plot the superconducting quasi-particle density of states. Yeah, for this you only need this file, and this can be done at various temperatures. In my plots, you have seen going from plus and minus. I basically use the same file and just multiply with the omega value with negative to see the gap between the basically from the minus energies to positive energies. Yeah, that's the way that I obtained that. And in the end, I'm not going to go to this because this you cannot do on Frontera, but if you have a Vesta installed on your local desktop or laptop, these are the steps to plot the cube files, and you can do the same for the Fermi surface, and you can do the same plots for the imaginary gap and also for lambda, and you can get some plots like this. Yeah, so this is the step that was documented here on how to do such plots, to make such plots. And finally, that's the same thing as you will find in the other file nodes on input variables. And at the end of the document, Harry has compiled some information on how you can some restarting options. One option is if, for instance, you have not finished the interpolation on the fine grid. Yeah, so you have not finished writing this EPH-MAT X files. So in that case, you will need to have these files from the interrupted run, and you will need to select to use this flag select qread true. Yeah, or otherwise if you have select FFT, otherwise this will be recreated. But this other file, this FMT till here, these are mandatory. And basically, if you have these files, you can just simply set up these input variables, and the code will continue from the interrupted Q point. If now you already have, and that's the option we have already discussed here, if you already have the EPH mat files, you only need to have this directory, which contains the eigenvalues, eigenfrequencies, the KQ map, and the EPH mat files. Yeah, and in this case, the important flags, basically you can set up all these flags that were originally true. You can set up them to false. In fact, the important one that you should really set up to false is this. Otherwise, it will first recalculate everything to write things on the file. In fact, not only calculate everything, but also write them on file. Yeah, so you want to avoid this. Okay, I think with this I finished going through the tutorial. So I'm happy to answer questions. We still have half an hour. So I can stop sharing the screen for now. Let me see if there are additional questions in the chat.
We can wait a bit, but we can also finish a bit earlier. I asked Feliciano and he said like maybe in 15 minutes or something, if there is no more questions.
So
I mean, of course, you should take the opportunity and ask question since Roxana.
Yeah, so everybody, yeah, I'm still around, so yeah.
Can I maybe ask again about this Padé approximant? So sorry that I'm nagging on with this. I just saw it in the output, and in the output it says something like Padé approximant of isotrope, I don't know, where is it? Convergence was reached for n equals 246 Padé approximants.
So that's basic. So that has nothing to do with the number of steps. It's basically how many. So this Padé method, in fact, it takes. That's roughly the number of imaginary Matsubara points, but I think we roughly take. I think the default right now is to take like 90% of the points on which you do the analytic continuation. So this is not an iteration. It's really, I think, I'm not sure if this is written how many. Let me look in the input output files. If it says every temperature, how many Matsubara points enter.
Maybe you can share so that we can see.
Yeah, I'm sharing, yes. So let me, I'm sharing this. Let me share the screen one more time. I think it is written. So if I look, for instance, here, I think this is MGB2 example, but let's look here at 10 Kelvin. So here we see how many Matsubara points we have. We have for this 10 Kelvin, we basically have 92 points. And the number of Matsubara points, or when we do the approximants, should be roughly 90% of this. And you see here that we had 82. It should really not say convergence. This we should change, because it's basically one shot. There is really no self-consistency. So in other words, it either works or it doesn't work. And then in principle, you can change this n in the input file.
Okay, thanks. That makes sense to me, and now I understand it better. And so how would one go from the Padé version to the non-Padé version? One simply does not put Padé equal to true.
No, in fact, you should always have Padé equal to true. First of all, this is very cheap. And second, unless you don't want at all the real access solution. If you don't want real access solution, then you don't need to put El Padé true. But if you want an analytic continuation, the first guess for the analytic continuation is provided by the Padé. But in fact, the code will stop. If you say L icon true and LPAD was false, it will stop and say, okay, also put LPAD true.
Okay, thanks a lot.
Welcome. Okay, there is a question. Are these files, Roman, the one that are for SCRIS-DEN? There was something with B. Okay.
Can you hear me?
No. Okay, there are different questions. Okay, yes, I can hear you. So
Okay, nice. So I was the first one was Simona, but I think we're both referring to the cube files.
So if you, so Simona, if you refer BSFs, I think these are for
this is XCRIS-DEN, yes. Mm-hmm.
I don't think we write in XCRIS-DEN format at this point. But in principle, yeah, you can change the source code just to make it in XCRIS-DEN format. And I don't know of any tool. Samuel, do you know of any tool to convert cube to BSXF?
No, but actually Leopold should be involved in those efforts, right? Maybe he knows.
Sorry, I don't know offhand, but we can check.
Then for the Fermi plots, why am I getting two cube files for the imaginary? Because there are two bands within the Fermi window for MGB.
Okay, because I just tried and I get three files for the Fermi surface. So the cube files for the Fermi surface, there are three.
Okay.
I mean, one of them seems to be like just some numerical thing. There's barely something in it.
Maybe it's because of the node converge things that we have, and maybe it happens that it has some points and it shows a third band.
Okay.
That's because the Fermi window, I think it's, let me see how many, in my case, I have two. I have 1 and 2. Let me share let me share the screen one more time. I only see two files, 1 and 2. You see at every 10, 15, I never.
Yeah, sure. Those are the cube files for the anisotropic gap, but there are those files that are called mgp2.fs. Oh yeah, you're having three as well. They're a bit to the left and up, like in the second column.
This is okay. This I didn't discuss. This is the free energy. This is if you want.
No. It's second. Yeah, in the second column, the third, fourth, fifth file.
Okay. I see. I don't know why there are three. I see. This is just the Fermi surface.
Yeah. I mean, I think I just plotted them. One of them really looks like a numerical thing. There's barely something in it. But I was wondering that at the Fermi surface file, it detects 3 bands, and then in the other ones just 2. So I was not sure if they were really connected or so.
Yeah, I guess maybe we should look. Yeah, I don't know this this part with the Fermi surface plot. I think this is a relatively newer implementation. So yeah, maybe there is something in there.
Okay, maybe there's another, I don't know, another cutoff in the code or so for them.
So
yeah, the cutoff is probably not fully consistent. I guess that would be the issue.
Okay.
Yeah, but that's a good point.
If you are really at the edge, maybe it's something like that, and it's.
Yeah, that's what I'm thinking. If there is something, yes.
But also keep in mind that the calculation we do are very unconverged here. So.
Yeah, sure. Yeah.
But that's still a good point. Why there we have 3 files and here just 2.
Yeah, they should be consistent.
Yeah. So this part with plot Fermi surface, it's outside the Eliashberg part. So it's.
Okay, but the rest work quite well, so they look nice.
So, but that's a good. I will write it down and we'll look into that.
Okay. Thanks.
Thank you.
Hi, Professor Margine. Can you hear me?
Yes.
I have a slightly theoretical question, not a technical one, related to the tutorial. So in the first part of the talk, I had a question if I can only use it for S-wave kind of theory.
Yeah, yes, I think I replied in the chat. Yeah, yes, the implementation.
So you said no. So does that mean like if I want to study topological superconductivity kind of thing, which let's say P-wave ordering, it's not possible to do this?
There is no implementation. The only implementation that is available in the code is for S-wave.
Okay, thank you.
Welcome. I think I see that I think there is something also in Quantum Espresso regarding maybe this cube and SCF, but I'm not sure. Besides. But I think the easiest thing would be maybe just inside EPW to give the format, CS format, maybe, I don't know. I don't really know the format of those files. I'm just talking right now to Leopold and I think Simona. Any more questions?
I also don't know. I haven't used the XSF format in quite some time, so I don't know so much about it.
I know that I think there are some files, maybe at least inside Quantum Espresso. I don't remember now in which directory, maybe with some utilities, where at least you can see the format, I think, of XCS.
It might be in PPSRC cube.f90. So I had a quick look.
Could be. Yeah. I don't remember at all.
So there's some info on.
Yeah, probably in some post processing. Yes, Any other issues with the exercises? Does it make sense? Hyunjung, is this your question or somebody asked the question? Does it make sense to plot band structures using the quasi-particle?
This is my question.
Including the superconducting. Oh, I don't know. I haven't looked at topological superconductors, so, but I guess one can at least give it a try and see. Are any announcements that we need to make for tomorrow? Samuel, Feliciano, do we have any announcements?
No, I mean, so tomorrow there will be the poster session. So basically there will be one lecture and one hands-on for the first 2 hours, and then a break, and there will be the poster session and then the poster prize. So we hope you're all going to come and present your research, and that will be also an opportunity. If you have more questions, I mean, we will be there. There will be 4 rooms, and so we will be split by topics, and so we will move from one to the other. So of course, feel free to discuss, and this should be more informal. So we hope we can have a nice chat, and that's it. We can discuss about anything, and yeah, I think we can close. I mean, it's been a long day. Right.
So very importantly, if you don't show up for the poster session and you're the winner of a poster prize, we will not give you the prize. So please do show up.
So maybe before closing the room, we should let the others know in the rooms that we are planning to close, just not to kick them out abruptly.
So just to answer about the Polaron, so yeah, exactly, Fish, I know answered this fine. So at the moment, it's not public, but it's being, of course, it's being developed. Yeah. Okay. Yeah, I don't know if Annecy, can you do the breaking, closing in 1 minute or something?
Yeah, sure.
And then, yeah, thanks. And then in 1 minute we will finish.
Okay.
So for Nilufar, you can see all the recording on the schedule. I will put the link. Oops, sorry, like this. So if you go on the schedule, you will see all the title for all the talks, and then next to it there is a recording. You just click. So obviously I haven't put the one for today, but I will try to do it tomorrow morning. Yeah. And then, I mean, basically, you will be redirected to the EPW YouTube page, so you can also subscribe or whatever. And then, whenever there will be a new video, then you'll get it. And for the error that was shown, so this is likely an issue that your input are not consistent. So typically, if you change the ECAT, for example, and you run the phonon code, and then you are trying to do, I mean, basically, if your phonon calculation is not consistent with the current SCF and EPW run, this is the type of issue you will get. So most likely you change the input, you change the ECAT, but you didn't change in the phonon calculation. So you have to redo the calculation. Yeah. Okay, so I think thanks everybody. I think we can finish. I'm just okay. Okay, see you tomorrow all. Bye bye.